Hello everyone, and welcome to my channel. My name is Nick Malloy, and today I'm going to provide you with a demonstration of the tutorial Planning a Homestead. This demonstration is based on the written instructions provided in Canvas. Sometimes we update them, so you should always use the written instructions when following along. Also, check Canvas for specific instructions on what you need to turn in at the end. Different instructors might have different requirements for this assignment. Setting up your workspace. Begin by setting up your workspace. Start by creating your project folder on your computer's desktop. You can call the project folder Homestead. This course uses a standardized folder structure to help you keep your data organized. Inside the project folder, you should create 3 subfolders: Original, Working, and Final. The Original folder is for storing unaltered copies of your data. The Working folder is either for working copies of your data or datasets you create during the project. The Final folder is for storing your outputs, such as tables, reports, and final map layouts. A quick note on the location of your outputs. Most file outputs that result from running the various tools should be stored in the project geodatabase. The Working folder is for specific standalone file types that you create or for working copies of the data. Saving to the Working folder will change the file type of the output. Don't save to the Working folder unless you are explicitly instructed to do so. Setting up a project in ArcGIS Pro. If it's your first time working in ArcGIS Pro, you might be prompted to sign in. On the ArcGIS Pro homepage, click Map under the New Project options. When the Create New Project window opens, name the project Planning a Homestead. It's fine to use spaces here. The next 2 steps are important, so don't skip them. Click the file folder icon so that the location is set to your Homestead folder on the desktop. Then uncheck the box next to Create a new folder for this project. The only time you would leave this box checked is if you started here and still needed to create a project folder. In this instance, you don't need to create a new project folder since you already did that earlier. When you create a project in ArcGIS Pro, several elements are automatically added to your workspace files. Open the project folder in Windows File Explorer to see what's inside. You should notice that beyond the 3 subfolders you initially created, Original, Working, and Final, a few other items are added to your workspace, such as a geodatabase and an ArcGIS project file. Never delete any of these files or folders from your workspace, or you run the chance of corrupting your project. In ArcGIS Pro, you can see these default files in the catalog pane by twirling open the folders. Spatial Analyst extension. The steps in this activity involve using the Spatial Analyst extension. Ensure this extension is activated by checking the licensing status under the application settings. It should say Yes next to Spatial Analyst. If it does, you're fine. You can move on to the next step. If it doesn't, you must configure your licensing options to ensure that the extension is activated. Decompressing a Tarball. Now you need to download the project data. You can find direct links to these datasets in the written instructions. Copy the data into your Original folder. Then decompress the zip file. You'll get a folder called Terrain Data. Delete the zip file so that only the Terrain Data folder remains. Open the Terrain Data folder. Inside this folder are 2 files that end with .tar.gz. This dataset is a double compressed format called a tarball. To fully decompress the file, you'll need to use 7-zip twice. So to unpack this tarball, I'm going to use 7-zip on the tar.gz file. To avoid confusion, delete the tar.gz file after you decompress it. I'm going to repeat these steps for the second tar.gz file. And I'll delete that original tar.gz file as well. What I have left are two files that end in .tar. Now you have to decompress these tar files the same way. Just use 7-zip to decompress them. You'll see a more dramatic result this time. The tar file decompresses many component files of the DDF file format. Go ahead and delete the .tar file. You won't need it anymore. Now I'm going to repeat these steps for the second .tar file. This unpacks another set of files in the DDF format. I'll also delete the second .tar file. As you can see, the DDF file format comes with many component files. It's important that you never delete any of these component files, or you will corrupt the data. You need all of these files for it to work properly. This is how it looks in Microsoft Windows. Let's see what it looks like in ArcGIS Pro. To see the data, you'll need to refresh the original folder. Then twirl open the terrain data folder. If you decompress the files correctly, you should see two files that end with the extension DDF. Using the Copy Raster tool. The next step is to convert these files into a raster data set that you will store in the project geodatabase. Right-click on the DDF file that has the number 9945 in the name. Then choose Export to Different Format from the list of options. This will open the Copy Raster tool in the Geoprocessing pane. Change the name of the output to Arcata North with no spaces. You can use an underscore instead of a space. Set the pixel type to 32-bit float. This means that each pixel will be able to hold a large number with decimal places. When you're ready, run the tool. The Arcata North digital elevation model should appear in the contents pane. Now I'm going to run this tool on the second DDF file that has the number 9946 in the name. I'll use the yellow file folder icon and browse to the terrain data folder. Change the name to Arcata South with no spaces. The rest of the parameters should be the same, but make sure that the pixel type is still 32-bit float. When ready, run the tool. The second digital elevation model should appear just south of the first one. Skill drill, inspecting the raster datasets. Take a moment to inspect the raster datasets. You'll need to open the properties and navigate to the source tab. In the written instructions, it asks, what is the digital elevation model's resolution or cell size? You can answer this by looking at the cell size. I can see that the cell size is 10. Depending on the linear unit, this is going to be either 10 meters or 10 feet. The pixel type and pixel depth are 32-bit float. This matches the copy raster settings we used earlier. Okay, let's look at the spatial reference information. The projected coordinate system is UTM Zone 10 Northern Hemisphere, and the linear unit is in meters, so now I know that the cell size is 10 meters, meaning this digital elevation model has a resolution of 10 meters since each pixel represents 10 meters on the ground. So one thing I noticed is that the name of the projected coordinate system didn't include the name of the datum. If you scroll down, you can check which datum it uses. It looks like this dataset uses the North American datum of 1927. The 1927 datum is not the most recent model optimized for North America. In the next step, you'll use the Project Raster tool to create raster datasets that use the North American datum of 1983. Skill drill, using the Project Raster tool. On the Analysis ribbon, click the Tools button to open the Geoprocessing pane. Type in Project Raster in the search box and open the tool. Use the drop-down menu and choose Arcata North as the input raster. I'll accept the default name for the output raster. Click the Select Coordinate System button and twirl open the projected coordinate system. Then go to UTM. Then NAD 1983. Choose UTM Zone 10 North. Change the resampling technique to bilinear. I find that using the setting gives you smoother results. Leave all the other settings and run the tool. The new raster dataset should appear in the Contents pane. Repeat these steps for the Arcata South digital elevation model. When you're done, remove the old Arcata North and South rasters from the Contents pane. In the next step, you will merge these two digital elevation models into a single raster dataset. Mosaic to new raster. Currently, I have two digital elevation models, one for Northern Arcata and one that covers the South. To perform a terrain analysis on this area of interest, I want to be able to work with a single raster dataset. In this step, I will combine these two raster datasets using the Mosaic to new raster tool. On the Analysis ribbon, click the Tools button to open the Geoprocessing pane. Type in Mosaic to new raster in the search box and open the tool. For the input, use both the Arcata North and Arcata South digital elevation models. Set the output location to the project geodatabase. This step often confuses students because they try to enter the file name here. You'll do that later. In this step, you are merely setting the location of the output. Just navigate to your project folder and select the project geodatabase. And that's it. Below that, you can enter the name of the output. Call it DEM. Since you are saving it to the project geodatabase, you don't need to add an extension. Now I'm going to set the pixel type to 32-bit float. If you don't do this, you'll lose a lot of data, so make sure it's set to 32-bit float. Digital elevation models use only one band. Enter 1 for the number of bands. And the cell size was 10. You can leave all of the other settings and run the tool. The result is a single raster dataset. I'm just going to check the properties to see that everything looks right. The spatial reference system looks correct. The number of bands, the cell size, and the pixel type and pixel depth look good as well. Once you're sure everything looks good, go ahead and remove the Arcata North and South layers from the Contents pane. Removing the Esri Basemap. There is one last step you need to take before starting the analysis. Take a moment to remove the default Esri Basemap from the Contents pane. My default basemap is called Dark Gray Base. yours will probably be something different, like World Topographic Map. Just right-click and remove the default Esri Basemap. You'll also need to remove the reference layer if you have one. Mine is called Dark Gray Reference, since it comes with a dark gray basemap. When you're done, you should only have the DEM loaded in the Contents pane. Using the Slope tool. In this scenario, you are conducting a site suitability analysis to find an optimal location for a homestead. Part of this fictional scenario is the assumption that there are no developed areas in this region. For our purposes, the city of Arcata does not exist, and the land is currently in its natural state. You will only consider terrain in this analysis. The criteria for this analysis is very simple. The goal is to find the largest area of land with a gentle slope that faces south. To start, you will identify areas with slopes that are between 1 and 5 degrees. On the Analysis ribbon, click the Tools button to open the Geoprocessing pane. Type in Slope in the search box. There are two options. Choose the Slope tool under Spatial Analyst. This tool is really easy to use. The input for the Slope tool will always be a digital elevation model. All you need to do is add the DEM as the input raster. I'm going to change the name so that it says Slope. The rest of the default settings are fine. Leave them as they are and click Run. A raster dataset representing slopes in degrees gets added to the map. In the next step, you'll use the raster calculator to identify slopes between 1 and 5 degrees. Skill Drill, Raster Calculator. The raster calculator should already be familiar to you. For a review on using the raster calculator, watch my video, Sea Level Rise Around Humboldt Bay. Okay, so I'm going to open the raster calculator and enter an expression that will get me slopes between 1 and 5 degrees. There are two conditions here, and both of these conditions need to be true. Whenever you enter multiple conditions in the raster calculator, each independent statement must be enclosed in parentheses. The first statement is slope greater than 1. Next, I'll use the AND operator. In the raster calculator, you use the ampersand symbol for AND. I'll enclose the next statement in parentheses as well. The statement is slope less than 5. I'll call the output slope 5 with no spaces. What I get is a raster dataset made up of ones and zeros. Anything assigned a 1 means that the conditions in the raster calculator are true. So the ones here represent areas with a slope between 1 and 5 degrees. The zeros represent everything else. So for now, we know that our homestead will be in one of these red areas. Next, we need to determine which slopes are facing south. Using the Aspect tool. In this step, you will find south-facing slopes using the Aspect tool. The Aspect tool uses a digital elevation model and calculates the direction each cell in the raster dataset faces. On the Analysis ribbon, click the Tools button to open the Geoprocessing pane. Type in Aspect in the search box. Here you'll see two options. Open the tool under Spatial Analyst. The input raster for the Aspect tool will always be a digital elevation model. So don't try to use the slope layer or it won't come out right. I'm going to name the output aspect. And that's it. I'll just go ahead and run the tool. What you see here is a raster surface model in which each pixel value contains the slope's azimuth. By this point, you should have already learned about direction and azimuth values. But to review, an azimuth indicates direction. It uses true north as a baseline and measures clockwise from 0 to 360. Azimuths are easy to use because one number defines each direction. Treating direction as a single number also makes it simple for the GIS software to use it in calculations. On this aspect layer, flat areas are set to -1 to indicate that they don't have an aspect. Skill drill, raster calculator. In this step, I'll locate south-facing slopes. The pixels on the aspect raster facing south will have values between 135 and 225 degrees. I can do this using the raster calculator. Okay, so I'm going to open the raster calculator and enter an expression that will give me aspects between 135 and 225 degrees. Just like the slopes earlier, there are two conditions here, and both of these conditions need to be true. Remember, when you enter multiple conditions in the raster calculator, each independent statement must be enclosed in parentheses. The first statement is aspect greater than 135. I'll make sure to close the parentheses. Next, I'll use the ampersand to enter the AND operator. I'll start with an open parentheses and type in aspect less than 225. Just going to widen this so you can see the expression clearly. I'll call the output south. Okay, everything looks good. I'll go ahead and run the tool. As before, I got a raster dataset made up of ones and zeros. Anything assigned a 1 means that the conditions in the raster calculator are true. So the ones here represent areas with aspects between 135 and 225 degrees. The zeros represent everything else. So for now, we know that our homestead will be in one of these red areas. Next, we need to determine which slopes are between 1 and 5 degrees and are also facing south. Intersecting through multiplication. Currently, you have two Boolean raster datasets. One represents slopes between 1 and 5 degrees, and one represents aspects between 135 and 225 degrees. Both of these rasters are made up of ones and zeros. Remember, in computer language, 1 equals true and 0 equals false. The ones on these rasters are areas we want to keep. We can find the optimal location by multiplying the two raster datasets together. Only the pixels where the overlapping conditions are true will result in a value of 1. Everything else will become a 0. Okay, so to avoid confusion, I'm going to take a moment to clean up my contents pane. I'll remove everything except for the dem, slope 5, and south. I don't need to see the slope and aspect layers anymore, and keeping them can lead to mistakes. Okay, so now I'll open the raster calculator and multiply the slope 5 times south. I'll call the output optimal. Okay, so what am I looking at? The red areas are places with gentle slopes that face south. These are the areas where I can establish my homestead. I'm going to remove the Slope 5 and South rasters from the Contents pane since I won't be needing them anymore. Raster to Polygon. In this step, you must convert the optimal raster dataset into a geodatabase feature class. You can do this using the Raster to Polygon tool. On the Analysis ribbon, click the Tools button to open the Geoprocessing pane. Type in Raster to Polygon in the search box. For the input, I'm going to use the optimal raster dataset. I'm going to call the output optimal locations with no spaces. I'll use an underscore instead of a space. Now, the next step is very important, so don't skip it. Uncheck the box next to Simplify Polygons. You don't want to simplify the polygons. So what does that mean? Remember, each pixel in a raster dataset is a square. Pixels leave jagged edges. When you simplify polygons, it smooths out the jagged edges. It looks nice, but it alters the area of the polygons. In a later step, we're going to do some area calculations, and we want them to be as accurate as possible. Okay, so it looks good. I will go ahead and run the tool. Now I have a vector layer representing the optimal locations for my homestead. Go ahead and remove the optimal raster from the Contents pane. You won't be using it anymore. Creating a definition query. Currently, I have a vector feature class that contains all of the potential locations for my homestead. The problem is that I also have areas that I don't want. In the raster dataset, these were the pixels that had a value of 0. I'll show you what I mean. Go ahead and open the attribute table for the optimal locations. Notice that there's an attribute called grid code. In the past, raster datasets were called grids because the pixels were arranged in rows and columns like a grid. So you can think of the term grid code like raster code. It's the values that were stored in the pixels of the raster dataset. In this instance, those values were either 1 or 0. So we want to keep the records with a grid code of 1 and remove the records with a grid code of 0. To do this, we can use what's called a definition query. Before I do that, make a note of how many records there are in the attribute table. If I look at the bottom, I can see that there are a total of 6,547 records. This total includes all the ones and zeros in the grid code. After we run the definition query, this number should get smaller. Let's see. Okay, so open the properties for the optimal locations feature class. On the left, choose definition query. I'll go ahead and add a new query. I'll enter the expression where grid code is equal to 1. I'll click apply to save the query. Then I'll click OK. Notice that the number of records in my attribute table got smaller. That's because all of the zeros are gone. The map changed as well. It only shows the polygons that have a grid code of 1. One thing to remember about a definition query is that the results are temporary. This is what is called a non-destructive change to the dataset. It looks and feels like a new dataset, but the original data is still there. It remains unaltered in the project geodatabase. A definition query is a good option when you want to work with a subset of the data, but you don't want to have to create a whole new data set. Okay, in the next step, we're going to finalize the location of the homestead. Sorting an attribute table. In this step, you will sort the attribute table to determine which polygon has the greatest area. This will be the location of the homestead. Open the attribute table for the optimal locations feature class. Double-click the shape area field. Whenever you double-click a field name, it will automatically sort the records either from high to low or low to high. Okay, it looks like it started from low to high. I want to see the highest value, so I'll double-click again. This reverses the order. Okay, so the largest piece of land is going to be my homestead. To select it, I'll just click the row on the left side. You can zoom into the selection by double-clicking. Okay, so this is what your homestead should look like. If you got a different result, it's likely that you made a mistake along the way. You'll need to backtrack to see where things went wrong. Hopefully you have the same result. Okay, so now I want to export this polygon into its own feature class. Just right-click on the optimal locations layer in the contents pane and choose Data, then Export Features. I'll call the output Homestead and click OK. I'm going to uncheck my optimal locations layer so I can see where this is. All right, I think my homestead is somewhere in northern Arcata, probably McKinleyville. In the next step, you'll conduct a viewshed analysis. Creating a hillshade. In the next few steps, you will create what is called a viewshed. A viewshed refers to an area or landscape that is visible from a specific location. This concept is crucial in various fields such as environmental studies, urban planning, and military operations, as it helps understand and analyze the visibility of geographical features or objects from a particular point or along a line of sight. Using a digital elevation model and other data, such as building heights, ArcGIS Pro can visibly represent viewsheds. This enables users to assess the impact of topography on visibility and plan infrastructure developments like buildings or wind turbines, and evaluate strategic viewpoints or coverage areas for surveillance and conservation efforts. To begin the viewshed analysis, we'll start with a hillshade to provide a visual sense of the terrain. On the Analysis ribbon, click the Tools button and type Hillshade in the Geoprocessing pane search box. Again, you'll see two versions. Use the one under Spatial Analyst. The input raster for a hillshade will always be a digital elevation model. Use the drop-down menu and choose DEM as the input. You can accept the defaults for the remaining settings and run the tool. What you'll get is a layer that provides a three-dimensional effect that gives the map reader a visual sense of the terrain. Feature to point. Earlier, I mentioned that to create a viewshed, ArcGIS Pro can use a DEM as well as other data, such as building heights. In this step, we're going to create a lookout tower for our homestead. Then we'll use the height of the lookout tower to determine the viewshed. On the Analysis ribbon, click the Tools button and type Feature to Point in the Geoprocessing pane search box, and open the tool. I'll use the Homestead feature class as the input. I'll name the output Tower. Be sure to check the box next to Inside. We want the tower to be located inside the Homestead polygon. When you're ready, run the tool. We now have a point within the Homestead polygon. Using the Geodesic Viewshed tool. Now that I have my lookout tower in place, I'm ready to create a viewshed using the Geodesic Viewshed tool. On the Analysis ribbon, click the Tools button and type in Geodesic Viewshed in the Geoprocessing pane search box and open the tool. For the input raster, choose the dim. For the input point or polyline observer features, choose the tower feature class. Twirl open the observer parameters group and enter the number 5 for the observer offset. This will simulate a lookout tower that is 5 meters high. You can leave all of the other default settings and click Run. The result is a raster dataset that represents all of the visible areas from the top of the lookout tower. So all of these places in orange are areas that can be seen. The analysis is now complete. You'll need to create a proper map layout to use as a figure in a lab report. For a review on how to create a map layout, you can watch some of my previous videos. Sea level rise in Humble Bay has a demonstration on how to create a small-sized map. Okay, that's it. I hope you enjoyed this demonstration of planning a homestead. If you want to see more videos like this, like and subscribe. Thanks for watching.